This is Lecture 2.2 of Math 108, Indirect Proof. In this video, we will learn the two types of indirect proof, namely proof by contraposition and proof by contradiction. Consider a claim in the form of a conditional sentence P implies Q. Recall that P implies Q is equivalent to its contrapositive not Q implies not P. Hence, one way to prove P implies Q is to prove its contrapositive not Q implies not P instead. This technique is called proof by contraposition. In such a proof, we begin with the assumption not Q and deduce not P. It will follow from contraposition that P implies Q. For example, consider the claim if AC is greater than or equal to BC and C is positive, then A is greater than or equal to B. Let P1 be the sentence AC is greater than or equal to BC, P2 be the sentence C is positive, and Q be the sentence A is greater than or equal to B. Then the claim is a conditional sentence whose antecedent is the conjunction of P1 and P2 and whose conclusion is Q. Observe that this is equivalent to the conditional sentence if P2, then P1 implies Q. A direct proof of this conditional sentence begins by assuming P2. We then proceed to deduce P1 implies Q. However, instead of giving a direct proof of P1 implies Q, we shall instead give a proof by contraposition. That is, we will show that not Q implies not P1. Hence, we assume that A is less than B. It will follow from contraposition and deduce that AC is less than BC. It will follow from contraposition that AC greater than or equal to BC implies that A is greater than or equal to B. Together with the first hypothesis, this will prove that if AC is greater than BC and greater than or equal to BC and C is greater than 0, then A is greater than or equal to B. For the proof, we combine both hypotheses in one sentence. Assume that C is greater than 0 and A is less than B. Then B is greater than A by the definition of less than. Since C is positive, it follows from the multiplication property of order that B times C is greater than A times C. Thus, A times C is less than B times C by the definition of less than. This proves that A is less than B implies that AC is less than BC. By contraposition, AC greater than or equal to BC implies that A is greater than or equal to B. Together with the first hypothesis, this proves that if AC is greater than or equal to BC and C is positive, then A is greater than or equal to B as required. The second type of indirect proof is proof by contradiction, also known as reductio ad absurdum. This technique can be used for a claim having any propositional form P. Recall that the argument P implies both Q and not Q, therefore not P, is a valid argument form. The statement both Q and not Q is a contradiction. Replacing P with not P, this argument form becomes not P implies both Q and not Q, therefore P. Hence, one way to show P is to show that not P implies both Q and not Q. That is, we begin by assuming not P and deduce a contradiction Q and not Q. It follows immediately that P must hold. Observe that in this proof, we do not know what statement Q is, since this is not given in the claim. It is up to us to determine whether or not such a contradiction has been deduced. For example, consider the claim if A is greater than B and B is equal to C, then A is not equal to C. Let P1 be the sentence A is greater than B, P2 be the sentence B is equal to C, and Q be the sentence A is not equal to C. Then the claim is a conditional sentence whose antecedent is the conjunction of P1 and P2, and whose consequent is Q. We begin the proof by assuming conditions P1 and P2. Our goal is to show condition Q. We shall do this by contradiction. Assume not Q, that is, assume that A is equal to C. We need to deduce a contradiction R and not R. It will follow immediately that A must not be equal to C, which is precisely condition Q. For the proof, we combine all our hypotheses in one sentence. That is, assume that A is greater than B, B is equal to C, and A is equal to C. By the transitive property of equality, B is equal to C and A is equal to C implies that A is equal to B. Since A is greater than B by the first hypothesis, it follows from the trichotomy axiom that A is not equal to B. Thus, we have deduced that A is equal to B and A is not equal to B. This is a contradiction. Hence, A is not equal to C as required. The next example is a variation of example 8. The claim is, if A is greater than B and B is equal to C, then A is greater than C. Let P1 be the sentence A is greater than B, P2 be the sentence B is equal to C, and Q be the sentence A is greater than C. Then the claim is a conditional sentence whose antecedent is the conjunction of P1 and P2, and whose conclusion is the statement Q. We begin the proof by assuming that A is greater than B and B is equal to C. Our goal is to deduce condition Q. Observe that Q is equivalent to the negation of not Q. Not Q is the statement A is less than or equal to C. This is the disjunction of the conditions A is less than C and A is equal to C. Hence, Q is equivalent to the conjunction of A is not less than C and A is not equal to C. We shall show that A is not less than C and that A is not equal to C. We will give a proof by contradiction for each of these claims. To show that A is not equal to C, we assume that it is not the case that A is not equal to C. In other words, we assume that A is equal to C. We deduce a contradiction R and not R. It will follow immediately that A is not equal to C. To show that A is not less than C, we assume that it is not the case that A is not less than C. In other words, we assume that A is less than C, and deduce a contradiction S and not S. It will follow immediately that A is not less than C. Therefore, A must be greater than C. We will leave the details of the proof as an exercise. Notice that the proof of the first part has been done in example 8. You have come to the end of lecture 2.2. You may now proceed to lecture 2.3. Thank you for your attention.